Hey, listeners, before we get into this episode, I have some fantastic news. My new book, Developing Mathematical Reasoning, Avoiding the Trap of Algorithms, is coming out, and we are having a book launch webinar to celebrate. This book spans from kindergarten to 12th grade, explaining in detail how algorithms trap students and what we should be teaching instead.
Join us at this free book launch webinar and you'll learn what the traps of algorithms are, how to avoid them, and so much more. You don't want to miss it.
We'll go live on March 18th, 7 p.m. Central. Grab your spot at mathisfigureoutable.com/book-launch.
That's www.mathisfigureoutable.com/book-launch. We hope to see you there.
Hey, fellow mathers, welcome to the podcast where math is figure-outable. I'm Pam, a former mimicker turned mather.
And I'm Kim, a reasoner who now knows how to share her thinking with others. At Math is Figureoutable, we are on a mission to improve math teaching.
Because we know that algorithms are amazing historic achievements, but they are not good teaching tools because mimicking step-by-step procedures actually traps students into using less sophisticated reasoning than the problems are intended to develop.
In this podcast, we help you teach mathing, building relationships with your students and grappling with mathematical relationships.
We invite you to join us to make math more figure-outable.
Hi there.
Hey.
I'm laughing because there's a note to you for time.
Oh, where it says this be short. Don't make this episode too long. Except, I a couple of weeks ago, I was in the frozen north of Alberta, and the teachers there drive farther, and they were like, "No, you could make the episodes longer."
No.
Like most people were happy when we keep them snappy. Let's snap today. All right, we're snapping.
Okay.
Today.
We're snapping. We're getting started. So last week we started talking about sequencing and sequencing. We didn't talk about sequencing strings. We talked about sequencing different kinds of tasks together to help build foundations of number. And so we talked about some young addition and subtraction last week.
Relationships.
So let's talk today about another area, and let's talk about multiplication division.
Yeah. So today we're going to focus on single digit multiplication division, kind of multiplication facts, and what does it mean to have early division, and how do you build the foundation for those things? Super important. Yeah. Go ahead.
Yeah. So if we say foundation, I think almost everybody would say a foundational thing that kids need to know first before they can do anything else is they need to memorize their multiplication facts.
Yeah, because kids, you can't do anything unless you have the building blocks. And so you've got to start with the building blocks and then go from there. That is very true. If my goal is to get kids really good, well, not really good, just even good. If my goal is that kids are going to repeat the steps of the multiplication algorithm, then we are all really clear that they're going to do a lot of single digit multiplication facts.
Yeah.
And we mentioned last week that for single digit addition or single digit subtraction, it would be super helpful if kids really owned the relationships. How do I say this? If I'm focused towards an algorithm, then kids need to know those single digit facts because they're going to do it over and over in the addition and subtraction algorithm. But you know what? In those addition and subtraction algorithms, kids can often get away with counting. And it looks fast enough that teachers don't even notice that they're counting one by one in those algorithms, even though they should be developing addition and subtraction, additive relationships, because they can often count. It's just single digits that they're adding together in column after column, or subtracting in column after column, that they can kind of do that, getting away with counting. But y'all, that is much harder to do in the multiplication algorithm. So if you are focused towards getting kids to do 1 through 49 odd of multiplication problems, where they over and over, they're doing all of these single digit multiplication facts, then it makes sense that you would say, go memorize those multiplication facts, get them down, because it's going to make everyone's life so much easier when you have to repeat all of those single digit multiplications in the multiplication algorithm over and over and over until you die. Yeah. Super true in the multiplication algorithm. Yeah. So what if the multiplication and division algorithms are not your goal?
Yeah. So what do we believe
Yeah.
are some foundational learnings for single digit multiplication? We believe that doubling is a massively helpful strategy. So you can double for 2, 4, and 8. So twos are doubles, 4 is double, double, eights are double, double, double. But not only that, if you know threes, then you can double those to get sixes. So doubling is a hugely helpful strategy.
And let me give you a specific while we're here.
Yeah.
An often missed fact, a most missed fact. If you test kids to see, out of all of those, often kids will miss 6 times 7. Like that's an often missed or most missed fact, 6 times 7. But if you know 3 times 7, which a lot of kids know, or they can find fairly quickly, 3 times 7, that's 21. Well, if 3 sevens is 21, bam, 6 sevens is double 21. Yeah. Almost everybody can double 21. And if you can't, start doubling with kids, and pretty soon they'll double 21 pretty readily. So 6 times 7 becomes a very figure outable fact if we've got that doubling down. Like you said, even 8 times 7, I can double 7 to get 14, double 14 to get 28, double 28 to get 56. Again, you might say, Pam, kids can't double 28. And I'll say, start doubling, like getting kids. That's what you're getting at right now, right? Is if we double with kids, then doubling, it becomes this major relationship that is a thread that runs throughout mathematics. Mathy people play with doubles. Sorry for interrupting.
No, it's okay. So in not only are doubling strategies helpful in single digits, they're also useful in larger numbers as well. So we're not just focusing on single digit, although that's what we're talking about today. The ones that we're going to mention are helpful outside of the single digit numbers. So another important foundation that we think kids can work with are making use of 10. So times 10, not only 4 times 10, but also times 10 can help you with times 5. So
yeah, you don't have to know your 5s if you know your 10s.
Yeah.
Nice.
Also 10s help with 9s. So you could subtract one group and get times 9. So making use of 10 is super important. We also think a foundational idea is partials. So using chunks that you know, which again helps outside of single digit facts. We also think really foundational idea is the commutative property. Mm-hmm. So within single digit facts, we know that sevens are stupid. Sevens are often
another often missed fact. Yeah.
And so
anything
if you understand
7.
the commutative property, then you can think about a strategy for the other factor. So those are some of our foundations that
which I just kind of threw out, right? Yeah. So when I said 7 times 8, 8 times 7 is an often missed fact. So don't do 7 times 8, do 8 times 7, and then you could double. That's just one strategy. You could also use 10, find times 10 and get rid of 2 of them to find 8 of anythings. But yeah, so if you don't like times 7, or if you don't like 7 times something, then do the other factor times 7, and that's super, super helpful. Yeah. Nicely done. So those are some of the major relationships that would build towards the major strategies for single digit multiplication. But like you said a minute ago, also they grow up and they lead to the major strategies for multi-digit multiplication, which then all leads to the connections for division. Super cool. Kim, what are some of the types of tasks? We started today talking about sequencing tasks. What are some of the types of tasks we think about when we think about creating sequences of tasks?
Yeah. So just like we talked about last week, we believe that there are some messing around types of tasks that are important. We also think that there's some ways to focus on strategy and analyzing strategy. And we think that there are some ways to practice. So often we would start with a task. We would build in some problem strings, some games, routines, and then we'd land with some sort of practice that kids can use.
Yeah, nice. So, Kim, let's dive into a sample kind of sequence of tasks that we might do to help develop early multiplication and division, and kind of talk about the categories and how they fit together, just to give everybody kind of an idea of what it could look like to do exactly what you just said. Like, what does it mean to start? Oh, go ahead.
Oh, I was just going to say, before you share a sequence that we've come up with, I wanted to say that last week, as you kind of talked through a sequence, that part of what I was thinking about is this is just much more fun and engaging and intriguing. Like when I think of a sequence of a textbook that it's like 4.1, 4.2, 4.3, it's like the same, same. And so maybe listeners, as you're thinking about the descriptions of the tasks that Pam is going to talk through, like picture what's happening with you and with kids and just the different feel that you take with these kinds of sequences.
Yeah, and I'll just pipe in the different kind of brain activity that's
Mm-hmm.
happening, that you sort of engaging kids in different ways is then therefore engaging, which is kind of a cool thing. So you mentioned three kind of categories. Something that's a little bit more messy. If I wanted to have something that's a little more, now I don't mean messy as in unstructured, unsafe. The kids don't know what to do. They're fumbling around. I just say, go discover mathematics. Come back when you do. It's not that. It's the kids are very clear on their task. They're clear on what they're supposed to do, what their role is. They're clear on how they're supposed to engage with what they're doing. But then as they dive into that, there are several kind of ideas that they're playing with. There's several mathematical relationships that could come up for them, and they might focus one direction or another. And part of the teacher's job is to be very interactive, circulating with kids in like a problem like the following. What if we were to take more of a product approach and say, hey, instead of talking about well, in fact, let me just back up a little bit. Often when teachers are trying to help kids learn their single digit multiplication facts, they'll say, all right, we're going to start with the twos and we're going to do all the twos. Then we're going to do the threes, then the fours, then the fives. And I might be, you might get a prize if you got all your sixes. Yay. You get the
Ice creams.
ice cream sundae, the topping on the sundae or whatever. And you get your sevens. Yay. You get a spoon to eat your ice cream, whatever. So notice that that's like a factor approach, but we're going to take a product approach to be a little messier. Instead of just like hammering one factor, what if we were to say, let's focus on, say, the number 12. And if grandma is going to build a garden and she's going to have a square foot garden and each plant takes a square foot. And so we give kids tiles, square tiles, and we say, hey, here's 12 tiles. What could grandma's rectangular garden look like? And then we're going to have kids create a 1x12 and maybe a 2x6. Another kid might create a 6x2. And as long as it's a rectangle, then we might say, well, like I'm circulating around as a teacher and I see a rectangle. I might say, how many can you find? Keep going. And how do you know if you have them all? That might sound familiar with last week's task where we threw out an addition situation like that, where we were looking at like lots of add-ins. Well, this time we want to look at like lots of all the factors. What are the factor pairs that come out of 12? Once kids are kind of solid on that, and again, we want to help them be strategic about how they are organizing so that they know if they have them all. That's a little bit of an extension task where other kids are just like thinking about, connecting area and perimeter and dimensions to factors and products. All of that's happening while they're also connecting that there are multiple iterations. I can make multiple rectangles for 12. Once we've got those kind of listed out, we've been sort of systematic so that we know if we have them all. Then we can say, all right, now I'm going to give you in partners, I'm going to give you other numbers. And I might give a certain partnership numbers like 9 and 13, go. And I might give another partner 24 and 25, go. And I might give another set of partners 36 and 33, go. And I might give let me do one more. I might not give a partnership 13 and 17. Why not, Kim? Why would I not give a partnership 13 and 17?
Because they're both prime.
They're both prime. And so what the only rectangles I'll come up with are 1x13 and a 1x17 or the commutative property there. And so I'm probably going to if I give them a prime, then I'm probably going to give them a really nice composite. But I also might naturally differentiate for kids by determining which partners I give them. If I've got kids that I know are going, and they really need a challenge, I might give them 36 because there's a lot of factor pairs for 36. I also might give them, I'm trying to think. What would be
you can give me 8.
You want me to give you 8?
I'll take 8. Yeah. You can have 36.
I was thinking you want 7 or 5.
I'll take it.
But I might give, a group, I might give them a prime and a composite. Yeah. Oh, by the way, in Canada, it's composite.
Oh,
was cracking me up a little bit.
Okay.
Yeah. I love regionalisms. I hope we never lose them. I think it's so cool. Anyway, so I might be judicious about the kinds of numbers I give different groups, not because I'm trying to dumb down for some kids. I'm trying to give them just on the edge of their zone of proximal development, just enough to keep them grappling, but not getting too frustrated.
Yeah.
And I also want to really challenge groups that are ready on the edge of their zone of proximal development.
Yep.
But then, Kim, then I want to have kids make posters for each of those where they've put the arrays they've created, those rectangular gardens they've created. Now we're just at that point drawing closed arrays. They're cutting out grid paper. But then I want to put those up on the wall. So now I've got the numbers 1 through 36 on the wall, each having a poster representing the different arrays that we could create. Now we're having now we're having a conversation about patterns where they can literally go, or I'll ask them, what do you see? Why do some numbers only have a 1 by? Which numbers are they? Hey, do you know? Mathematicians call those prime. How about if we have some numbers that have, 1 by. If they have a 1 by, they could be odd. If they only have a 1 by, then they're prime, right?
Yeah.
Oh, everything has a 1 by. What am I saying? Help me. Even are going to have a 2 by.
Yes.
Odd won't have a 2 by. There
Correct.
we go. Ha! So,
but in that, kids,
clean that up for me, Kim. Say that right. Say that better for me.
Evens will have a 2 by, but kids will find that pattern. This is not you telling all these things. You're putting them up in front of kids that they've made, and you're sitting back going, notice. What do you notice? And a kid will say, wait a second, some have a 2 by and some don't. Why? What do you notice?
And then we can drop in the vocabulary just in time.
Yep.
Oh, you're noticing that there's some even numbers and the odd ones don't have a 2 by. Yeah, that's what we call those. Yeah. And you're noticing that there are some numbers that only have a 1 by. They don't have anything else. Oh, yeah. Mathematicians call those prime. And some people are really interested in prime numbers. Do you see a pattern? Like, is it every certain number? There's not a pattern for every, whoa. Do you know there's not a pattern? Like, people are still looking for patterns for primes. And then students will notice square numbers and which numbers had squares. Is there a pattern for square numbers? Lots of things, again, like nicely said. That's an example of what we mean by messy. It's messy because kids can notice things and we can pull those patterns together, but they can notice different patterns. That's the messy part of it, right? So there's an example of kind of a messy thing. Another example of a messy thing could be where we want to get kids thinking about skip counting on an open number line, where we could have them thinking about a race. And if we have a race that's so long and we're going to put aid stations at certain points, then if it's every, say if it's a 70-kilometer race and we're going to put race stations every 7 kilometers, like where would we put them? And we could have kids really be thinking about multiples on a number line and what it looks like to have sort of skip counting on a double open number line. We could ask them certain questions about where they would go and how they know. We could also build a ratio table with kids by literally starting to plan a party. And we could say, well, hey, if we're planning a party and these are the things that we need, fill in the table for different numbers of things that we need at the party. And kids could ask and answer questions about that party planning, all around the idea of sort of building a different model, the model of a ratio table. Notice that in this messy sort of category, I'm mentioning 3 major models. One of them was the area model, where we gave kids tiles and we're having them create the grandma's garden. Another one is an open number line with the race stations. And another one is the ratio table, where we're planning parties. So often we like to build models by having kids in situations where the model is helpful to really make sense of what's happening in the situation. And that model starts to emerge as a mathematical model that we can use to build more relationships.
Yeah. Also in this messing around time, that you're building a model, but you also are steeped in a context, and you're building some things that you can come back to all throughout the year.
Lean back on. Yeah. When kids want to do something, say on a ratio table, you could be like, oh, wait, if it's the number of cakes, do you have to, let me get a better example. If I've got bags of cups for the party and I have so many cups, if I add the bags, if I add 1 bag, do I just add 1 cup? Now I got to add all the cups in the bag. So you can reach back to that context to help kids make sense of the model when the context isn't there. If you've developed a really nice context. Yeah, that's nicely said. So those are some examples of things that you could do that are kind of messier, but we would want to sequence those with tasks in that category where we're building strategies. When we're building strategies, that's where problem strings come in, where we're going to build really the relationships that lead to strategies becoming natural outcomes. But we can also do things like put a multiplication chart in front of students. Now, not as a retrieval device where I say, oh, you can't memorize your multiplication facts, so I'm just going to give you this chart and you just go drag your fingers to the thing and you just retrieve that fact. Y'all, if for a retrieval device, how about if we just give them a calculator? We don't love retrieval devices. We'd much rather have kids build their multiplicative reasoning. One way we can do that is putting a multiplication chart in front of them and asking kids, what patterns do you see? And when they see patterns on a multiplication table on that chart, then we can say, like you're thinking that if we look at this row, it's all zero. Why would that be? Oh, because you're multiplying by zero. And if we look at this, Kim, what's another pattern on a multiplication chart that we might want kids to pull out?
The twos, that they're going to all end with an even number.
Nice. One more. What's one more cool pattern?
Fives are going to end in a 5 or a 0.
And they're also going to be half of the 10 row. Yeah. Yep. So if we look at the 10 row or the 10 column, the fives are going to be exactly half of those. Yep. So lovely patterns that can come out on multiplication charts. We can also then use those 3 models that we began to develop in the messier tasks. We can put student strategies on those models and smudge out part of their work. And then say to students, hey, like fill in the smudges. And now that you've filled in the smudges, what was this kid doing to solve that problem? Like in this ratio table, you filled in the smudges. Here was the problem they were solving. What relationships did they multiplied by 10 and cut it in half to get 5? And this kid, what did this kid do? Oh, they multiplied by 10 and cut it in half to get 5. What did this kid do? Oh, they multiplied by 10 and cut it in half to get. So you don't have to know your fives if you know your tens. You could just, that seems like a helpful strategy. How are we starting to develop the foundation for that strategy? We've given kids a model. We've smudged out part of the work, and then we're analyzing what the kid was doing in that particular model. Another example could be an open array. We've now got an open array where we smudged out work, and we might see a something by 10 that's cut in half to that something by 5. And when they fill in those blanks, they're like, whoa, like I can model that strategy in the ratio table I just talked about, but I can also represent that in this open array. So the same strategy on different models, all developing kind of these undercurrent relationships that build the foundations for strategies. When we've built one of these major strategies, or at least when we've started building it, we've put some words around it, we can create anchor charts for those strategies. So I would want to have done some of this messy stuff and some of these smudge problems to analyze, looking at the patterns on the multiplication table, doing problem strings to get the strategies to be happening. And then once we've put words to it, now I'm creating a strategy anchor chart that says, you don't have to know your fives if you know your tens. Like 5 is half of 10, and I could represent that on a couple of different models. Hang that on the wall. Now, when kids are messing around, they're trying to make those single-digit facts and bigger numbers. When they're trying to make those more automatic, they could refer to that anchor chart. That's not the only reason we create an anchor chart. We create anchor charts to anchor the learning. By putting words to the relationships that are happening, kids get more clarity around it. But now also we can refer to it because it's on the wall. We can continue to get to cinch those ideas. So those are some ideas of things that we can do to help kids build foundations for strategies by analyzing patterns and strategies. The third category that you talked about, Kim, is we do want kids to practice. We just don't want it to be mindless practice. It's not practice to rote memorize. It's not practice with a song or a rhyme or a rap. It's practicing really in maybe in a few ways. So here's maybe our favorite way. We really like two kinds of practice, two kinds of cards to practice single-digit multiplication facts. One of them is similar to the cards that I talked about in last week's episode for single-digit addition facts. We call them hint cards, where it looks kind of like a flashcard. And ideally, you'd interview kids and you would say, here's a fact, 7 times 8. And when the kid says, and they have to fuss too long and they're doing something unsophisticated to find it, then I put that in the pile, facts I don't know, yet. But if I show you 3 times 4 and the kid just is like 12 and they're like they know it pretty readily, I put that in the facts, they know. Well, then we just take that smaller deck of cards that is the facts we don't know yet, and we help kids come up with good hints. We look to that anchor chart that had the relationships on it, that has those strategies we started to build, and we're like, what would be a good strategy to use to figure this one that you don't know? And now when I flash you those hint cards, now you can use that hint just enough, not too much. Don't give it away. Don't make it too laborious that we have to like spend all of our time trying to figure out what the hint is. Either way, it's just enough of a hint that works well for me. We might even erase the hint I chose because it wasn't working well and choose a better one. But we create these hint cards. And now I want kids practicing with those hint cards, but they're practicing using reasoning and relationships. We want the facts at their fingertips, but we want more than that. We want those relationships also. But Kim, I got to tell you, I just saw the other day the completely created array cards. So we've created a set of array cards, y'all, that are so cool. Let me describe what these look like. So we had the hint cards I talked about, but the array cards look like closed arrays. So if I was looking at, say, the fact 4 times 8, it would have 4 rows by 8 columns. And I'm looking at a grid. And in the middle of it, it would say 4 times 8, 8 by 4. And on that, I see a grid, 4 by 8. Then on the back of that card, it says, ready, everybody? 32. And the back is blank. There's no grid lines. So the back is an open array, but it is spatially correct. It's a 4 by 8. On the front is a closed array that says 4 by 8, 8 by 4. So if we're playing with those, we can play several different versions of those, and sometimes we'll do a whole episode on those cards. But I can literally look at that 4 by 8 on the front, and I can ask myself, what's the area? Flip it over. Sure enough, it's 32. When I get a bit more advanced, I can play only looking at the backside. So now I'm only looking at open arrays that simply have the area on it. So Kim, if you're looking at an array card right now, no grid lines, it's the backside, only has the area listed, and it says 36. What are you looking at on the card to help you know what, what is it? What's the card?
I mean, I think I'm looking at the shape to start with. Like, is it compact? Is it square? Then it might be the 6 by 6. Is it long and skinny? Like really long and skinny? And then it's a 1 by 36 or maybe a 2 by 18. But the shape, the dimensions of it's going to help me figure out what the dimensions are.
Yeah, nice. What if it's not a square, but it's kind of close to a square?
Then it's probably going to be the 4 by 9.
Nice. See, there's like lots of, look at all the reasoning that can happen. This is a brilliant set of cards that we can use with students that's kind of self-differentiating.
Yeah.
Again, we'll do a whole episode on that later.
Yeah.
So Kim, this sequence that we've just talked about, you could do these kinds of messy tasks, these kinds of building foundations for strategy where you analyze strategy tasks. You could do these kinds of practice things with your kids, and you can sequence those with problem strings to really help kids build single-digit multiplication and division relationships with students.
Yeah, I'm going to go back to the list that I described at the beginning, that if you are a very traditional teacher, then your foundations are memorize facts. But as you were describing, I was thinking about kind of the bigger mathematics that's happening here. We talked about doubling with different numbers. We talked about 10 and 5 and 9. We talked about partials. We talked
partial
about
products,
or
quotients.
Commutative property. We built models. So not only are those essential for facts, but they're also giving you a very firm foundation for what will be to come for these students outside of facts.
Nicely. In so many different ways.
Yeah.
Multiplicative reasoning, area, geometry, like lots and lots of brilliant properties with commutative property. Yeah. And distributive property.
Yeah.
With the partial products and partial quotients. Yeah. Nicely done. So, and y'all, if you don't want to create this sequence on your own, but you'd like to check out one that we've created, check out our Foundations for Strategies product with Hand to Mind. That is the single digit multiplication and division product that has tasks like this, all sequenced nicely for you in an easy to read format. We're super proud of that. If you don't want to create your own, you want to save a little time, then check out our Foundations for Strategies. Y'all, thanks for tuning in and teaching more and more real math. To find out more about the Math is Figureoutable movement, visit mathisfigureoutable.com. Let's keep spreading the word that math is figureoutable. Hey, listeners, don't forget, go to mathisfigureoutable.com/book-launch to register for the free Developing Mathematical Reasoning, Avoiding the Trap of Algorithms book launch webinar taking place on March 18th. Y'all, I'm going to be there. It's going to be cool. You do not want to miss this. Totally free. Come join us. mathisfigureoutable.com/book-launch. We'll see you there.